Tonight, if you looked up, some of the light reaching your eyes would be older than the ground itself. It left its galaxy before the sun was born, before anyone was here to look back at it. And here is the strange part. Every galaxy you can see began as almost nothing. A thin haze of gas, a whisper of matter spread so smoothly across space that you could have drifted through it without noticing. Over the quiet hours ahead, we are going to follow that haze as it slowly becomes a galaxy. Before we start, I would love to know where you are listening from and what the clock reads in your room right now. Leave it below. I like picturing all the different lamps and windows this story floats toward. Now, settle in and let your breathing slow with mine. So let's slow down. There is no hurry tonight. Nothing in this story needs to be finished or solved or remembered in the morning. You are allowed to drift in and out of it, the way you might drift in and out of sleep on a long train ride, catching a sentence here, a picture there, letting the rest move past you like fields in the dark. The universe took something close to 14 billion years to make the galaxies we see. So there is no reason for us to rush through the telling of it in a single evening. We will take our time. We will pick up one idea, turn it over gently, set it down, and reach for the next. If your eyes are already heavy, that is good. You don't need to understand all of this. You only need to let it carry you somewhere calm and wide and old. This is a story about how galaxies form, which is really a story about how almost nothing becomes almost everything. How a faint fog of gas, spread evenly through the dark, gathers itself over billions of years into the bright, wheeling cities of stars we now take for granted. It is one of the slowest stories ever told, and that makes it, I think, one of the best ones to fall asleep to. Let me begin somewhere familiar. Imagine you are standing outside on a clear night, far from any town. The kind of night where the sky doesn't end at the rooftops, but seems to keep going, deeper and deeper, until your eyes can't follow it anymore. You tip your head back, and if the air is dark enough, you might notice something many people never see at all. A soft, pale band of light, stretched in an arch across the whole sky like spilled milk, or a faint smear of cloud that never moves. People have been seeing that band for as long as there have been people. The Greeks called it a river of milk. Other cultures saw a road, a backbone, a path that the dead walk along on their way somewhere else. We still carry one of those old names with us. We call it the Milky Way. For thousands of years, nobody knew what that band actually was. It was beautiful, and it was strange, and it was simply there. It was only in the year 1610 that a man in Italy named Galileo Galilei pointed a small, crude telescope at it, a tube barely better than a child's toy by today's standards, and saw something that no one had ever quite been able to prove before. That soft river of light was not a cloud at all. It was made of stars, countless stars, packed so closely and so far away that the eye blurred them into a single glow. The river was grainy. It was crowded. It was, in a sense, a crowd of suns seen edge-on. Hold on to that image, because it is the whole story in miniature. When you look at that pale band, you are looking at our own galaxy from the inside. You are sitting in the middle of one of those wheeling cities of stars, looking out through the thick of it. The Milky Way is not just a stripe in the sky. It is the place we live. And tonight we are going to ask the slowest, deepest question we can about it. Not just what it is, but where it came from, how something like this came to exist at all. Now think about this for a second. There are something like 100 billion stars in our galaxy, maybe more. And our galaxy is only one among many. Just how many is something astronomers still argue about. Because the faintest, most distant galaxies are so hard to count. The honest answer is somewhere in the hundreds of billions at least, and by some estimates, as many as 2 trillion. The number is so large, in any case, that it stops meaning anything. Which is fine, because you don't need it to mean anything tonight. You only need to feel the shape of the question underneath it. Every one of those galaxies had a beginning. Every one of them was, at some point in the deep past, not yet a galaxy. And the question we are going to follow, slowly, gently, all the way down, is this. How do you get from a universe with no galaxies in it at all to a universe filled with them? How does the light in that soft band over your head come to be there, waiting for you to look up? That is the mystery, and it is a real one. For most of human history, people assumed the heavens had simply always looked this way, fixed and eternal, the same stars in the same places forever. It is a comforting idea in its way. But it turned out not to be true. The sky has a history. The galaxies have ages. They were born, and they grew, and they changed, and some of them collided and merged into new shapes. And all of this happened over spans of time so long that a human life, or all of human history together, is barely a single frame of it. We are going to walk through that history tonight, one careful step at a time. And we are going to start by going back, as far back as we can possibly go. But before we travel back billions of years, let me stay in the present for just a little longer, because there is a piece of recent history worth telling. The story of how we even learned that other galaxies exist. Because for a very long time, we didn't know they did. Picture the world a little over 100 years ago, the early 1920s. Telescopes had grown enormously since Galileo's little tube. There were great observatories perched on mountaintops, with mirrors as wide as a dining table, gathering faint light from the dark. And astronomers had been finding, scattered across the sky, strange faint smudges they called nebulae. The word just means cloud or mist. Some of these smudges were genuinely clouds of gas inside our own Milky Way, but others were peculiar. They had a soft spiral shape, like water circling a drain, or like cream stirred once into coffee and then left to settle. And nobody could agree on what they were. Here was the heart of the argument. One group of astronomers believed that the Milky Way was the entire universe, that our galaxy was everything there was, a single vast island of stars floating in an endless empty void, and that those little spiral smudges were simply small objects inside it, nearby clouds, minor things, part of our own neighborhood. The other group thought something far stranger and far grander. They thought those spirals were not small and nearby at all. They thought each one was a separate galaxy, an entire Milky Way of its own, unimaginably far away, so distant that all its billions of stars blurred into a single faint smear, just as Galileo's river had blurred until he looked closely. Island universes, some people called them. Whole other islands of stars, scattered through a darkness much larger than anyone had dared to imagine. This disagreement came to a head in a famous public discussion held in Washington in the spring of 1920 between two astronomers named Harlow Shapley and Heber Curtis. People sometimes call it the Great Debate. Shapley argued that the universe was essentially just our one galaxy. Curtis argued for the island universes, the idea that the spirals were far-off galaxies in their own right. And here is the honest, human truth of it. At the time, neither man could prove his case. They each had good arguments and good evidence, And they each had blind spots, and the question simply could not be settled with the information they had. They went home, and the argument stayed open. Imagine that. The single most basic question about the size of everything, whether our galaxy was the whole show or one of countless others, and the best minds of the age genuinely did not know. What broke the deadlock was not a clever argument. It was a measurement. And it came from a tall, pipe-smoking, rather grand astronomer named Edwin Hubble, who was born in 1889 in Missouri, and who came to work at the Mount Wilson Observatory in the hills above Los Angeles. Mount Wilson had, at that time, the most powerful telescope in the world, the 100-inch Hooker telescope, a giant glass eye that could gather light too faint for any instrument before it. And in 1923 and 1924, Hubble turned that great eye on one of the most famous of the spiral smudges, the one in the constellation Andromeda, a faint oval glow you can actually still see with your own eyes on a dark night if you know where to look. Now, here is the thing that made it possible. To prove the spirals were far away, Hubble needed a way to measure distance across space. And distance is one of the hardest things in all of astronomy to pin down. You cannot stretch a tape measure to a star. But there was a tool waiting for him, and it had been forged by someone whose name deserves to be said slowly, because she did not get nearly enough credit in her own time. Her name was Henrietta Swan Leavitt. Leavitt was born in 1868, and she worked at the Harvard College Observatory in the early years of the 20th century as one of a group of women hired to do the painstaking work of measuring and cataloging stars on photographic plates. They were paid very little. They were called computers, because computing back then was something a person did, not a machine. And Leavitt, working through plate after plate of a small companion galaxy called the Small Magellanic Cloud, noticed a pattern in a particular kind of star. These were stars that pulse, that brighten and dim and brighten again on a steady rhythm, swelling and shrinking like a slow heartbeat. We call them Cepheid variables, and Leavitt discovered something quietly miraculous about them. The brighter the star truly was, the slower it pulsed. The dimmer ones blinked quickly. The bright ones took their time. Let me slow down here, because this is one of those small ideas that turns out to unlock the universe. If the rhythm of a star tells you how bright it truly is, then you have a kind of cosmic lighthouse. Think of it like this. Imagine you are standing at one end of a long, dark beach at night, and far down the sand you see a lantern. You cannot tell how far away it is just by looking. A dim lantern close up and a bright lantern far away can look exactly the same to your eye. But now imagine that every lantern of a certain kind always burns at the same known brightness. The moment you know how bright the lantern truly is, you can work out how far away it must be, simply from how faint it appears to you. The dimmer it looks, the further it sits. Leavitt's pulsing stars were exactly those lanterns. Their rhythm told you their true brightness, and their true brightness, compared with how faint they looked from Earth, told you their distance. So when Hubble found one of these pulsing stars inside the Andromeda spiral, and timed its rhythm, and worked out how bright it truly was, and compared that with how impossibly faint it appeared in his telescope, the answer came back staggering. Andromeda was not a small cloud inside our galaxy. It was almost unimaginably far beyond it, so far that its light had been traveling for hundreds of thousands of years, and in fact, we now know for about 2.5 million years, before it reached his photographic plate. Andromeda was a galaxy, a separate island of stars. The debate was over. Curtis had been right about the spirals, and in a single measurement, the universe became vastly, dizzyingly larger than almost anyone had believed. I want you to sit with that for a moment, because it is a beautiful and slightly vertiginous thing. Within living memory, within a single human lifetime, our picture of everything went from one galaxy to billions of galaxies. The night sky did not change. The faint band overhead stayed exactly where it had always been. What changed was our understanding of how deep it went. We had been like someone who thought their house was the whole world, opening the front door for the first time and discovering an entire continent stretching away beyond the porch. And once you know that galaxies are out there, in their billions, the old comfortable assumption falls apart. The assumption that things had always been this way. Because Hubble was not finished. Over the next few years, working with the light from many galaxies, he found something even stranger than their distance. He found that they were moving. Almost all of them were moving away from us. And the further away a galaxy was, the faster it was racing off into the dark. Now, let's slow down, because this is the hinge on which the whole night turns, and it is easy to skip past too quickly. The galaxies are running away from us. That sounds at first like it might mean we are sitting in some special repellent spot, that everything is fleeing from us in particular. But that is not what it means at all. Let me give you a gentler picture. Imagine a loaf of raisin bread dough, sitting on a kitchen table, slowly rising. The raisins are scattered through it. As the dough swells, every raisin drifts away from every other raisin. If you were a raisin, you would see all the other raisins moving away from you, and the ones furthest away would seem to move fastest, simply because there was more dough swelling up between you and them. No raisin is special. No raisin is at the center. The whole dough is just expanding everywhere at once, carrying every raisin apart from every other one. That is what Hubble found the universe doing. Space itself, the dough between the galaxies, is stretching. The galaxies are the raisins, riding along. And here is the quiet, world-changing consequence of that. If the universe is expanding now, if everything is drifting apart, then in the past everything must have been closer together. Run the film backwards. The dough unswells. The raisins crowd in. Go back far enough, and everything that exists, every galaxy, every star, every atom in your body, was packed into a single, almost unimaginably hot, dense state. There was a beginning, a first moment. We have a slightly clumsy name for it now, one that started as a bit of a joke and stuck. We call it the Big Bang. Let me reassure you about that name, because it gives people the wrong picture. The Big Bang was not an explosion in space, like a firework going off in an empty room. It was not a bang at all, and there was no empty room for it to bang into. It was the beginning of space itself, and of time itself, expanding everywhere at once. Not matter flying out into a void, but the void itself stretching and cooling. It is one of the hardest ideas in all of science to hold in your head, and you do not need to hold it firmly tonight. You only need the gentlest version of it. Long ago, everything was hot and crowded and small. And then it began, very steadily, to grow and cool. Everything since has been the story of that cooling, including, eventually, the galaxies. So now we have our true beginning. Let me take you there, as far back as we can sensibly go, to a universe so young there were no stars in it at all. No galaxies, no planets, nothing you would recognize, just heat and light and a thick, glowing fog. We are going back about 13.8 billion years. That is the age of everything. And in those first moments, the universe was unrecognizable, in the very earliest fractions of a second. conditions were so extreme that the ordinary words for things barely apply. It was hotter than the inside of any star, denser than anything we can build or imagine. There were no atoms, because it was far too hot for atoms to hold together. There was just a seething soup of the smallest building blocks of matter, jostling in a sea of intense radiation. As the universe expanded, though, it cooled. And cooling is the gentle engine that drives this entire story. Each time the universe cooled past a certain point, something new became possible. Things that could not exist in the heat could suddenly form in the calm that followed. Within the first few minutes, as the soup cooled, the very lightest atomic cores began to assemble. This is one of the loveliest and best-tested chapters of the whole history, and it has a name that sounds grander than it needs to. We call it Big Bang nucleosynthesis. All it means is that, in those first few minutes, the simplest atomic nuclei were forged. The universe became a kind of brief, gentle furnace, cooking up the raw ingredients of everything to come. And it made, overwhelmingly, the two lightest elements. Hydrogen, the simplest of all, just a single particle of positive charge. And helium, a little heavier, a trace of lithium, lighter still in quantity. And essentially nothing else. No carbon, no oxygen, no iron, no gold. None of the rich variety of elements that make up the world around you or your own body. In the beginning, the universe was almost entirely hydrogen and helium, and it would stay that way for a long, long time. I want you to hold that fact close because it matters more than it sounds. Everything that you are made of, the calcium in your bones, the iron in your blood, the carbon in every living cell, none of it existed yet. The early universe simply had no way to make it. The ingredients for you, for the earth, for life, would have to be cooked up much later, inside stars that had not yet been born. But to make those stars, you first need galaxies for them to be born in. And to make galaxies, you need something to gather the gas together. So let us keep cooling and keep waiting and see what happens next. For roughly the first few 100,000 years, the universe stayed too hot for atoms to form properly. The hydrogen and helium nuclei were there, but they could not hold on to their electrons. The electrons were too energetic, too fast, zipping freely through everything. And this had a strange effect. Light could not travel freely. It kept bumping into all those loose electrons, scattering off them, the way the beam of a flashlight gets lost and diffused inside a thick bank of fog. The whole universe was glowing, but it was opaque. If you had somehow been there, you would not have been able to see anything clearly. Just a blinding, formless, fiery brightness in every direction. A cosmos of fog. And then, about 380,000 years after the beginning, the universe cooled past another quiet threshold. It became cool enough, at last, for the electrons to settle down and join with the nuclei, forming the first complete, stable, neutral atoms, whole hydrogen atoms, whole helium atoms, and the moment that happened, the fog lifted. With the loose electrons gone, light was suddenly free to travel in straight lines across space, uninterrupted for the first time. The universe became transparent. It became clear. That moment of clearing left behind a kind of fossil, and it is one of the most extraordinary things we have ever found. The light that was set free when the fog lifted is still traveling through the universe today, all these billions of years later, stretched out by the expansion of space into a faint, cold whisper of radiation that fills the entire sky. We call it the cosmic microwave background. It is the oldest light there is. It is the afterglow of the early universe, the gentle warmth left over from when everything was young and clearing. And here is a small, strange, homely fact to fall asleep on. A tiny fraction of the static, the snow, that used to appear on old, untuned television sets was actually this ancient light, this whisper from the dawn of everything, arriving in your living room. The birth cry of the cosmos, showing up as faint specks on a screen. The story of how we found that light is worth a gentle pause, because it is one of the great accidents of science. In 1964 and 1965, two researchers named Arno Penzias and Robert Wilson were working at Bell Laboratories in Holmdel, New Jersey, with a large horn-shaped antenna. They kept picking up a faint hiss of background noise, a steady hum that they could not get rid of no matter what they did. They cleaned the antenna. They even, famously, scrubbed away the droppings of pigeons that had nested inside it, suspecting the birds might be the problem. But the hiss remained, coming from every direction in the sky, day and night, equally. It would not go away because it was not a fault. It was the universe itself, gently glowing. They had stumbled, almost by accident, onto the oldest light in existence, the very afterglow that other scientists had predicted years earlier might be out there. It is one of my favorite stories in all of science. Two people looking for the source of an annoying noise and finding the echo of creation instead. Now, here is where our story has to make a turn, because so far I have told you about a universe that is almost perfectly smooth. After the fog lifted, the cosmos was filled with a thin, even haze of hydrogen and helium gas, spread out across space with astonishing uniformity. And that uniformity is, at first, a problem, a real one. Because if matter had been spread perfectly evenly everywhere, with no lumps, no clumps, nothing thicker in one place than another, then galaxies could never have formed at all. Gravity needs something to grab onto. It needs a starting lump. A perfectly smooth universe would have stayed smooth forever, a featureless mist, drifting apart as space expanded, growing thinner and colder and emptier, with nothing ever gathering, nothing ever igniting, nothing ever becoming a star. No galaxies, no suns, no planets, no us. Just an endless, even lonely fog. So the great question becomes this. If the early universe was so smooth, where did the lumps come from? What gave gravity something to grab? Let's slow right down here, because the answer is subtle and lovely, and it rewards a little patience. The early universe was smooth, yes, but it was not perfectly smooth. When we look very, very carefully at that oldest light, the cosmic microwave background, the afterglow of the fog lifting, we find that it is not exactly the same temperature in every direction. There are tiny variations. Places that are a hair warmer, places that are a hair cooler. Differences so small they are almost nothing, a fraction of a degree. Ripples you would never notice without the most delicate instruments ever built. But they are there. The universe came out of its beginning with the faintest possible texture, the gentlest unevenness, like the almost invisible grain in a sheet of handmade paper, or the soft modeling on the surface of still water before the wind touches it. Those tiny ripples were the seeds. The slightly denser patches had a little more gravity, and gravity, given enough time, is patient and relentless. A region with a touch more matter pulls in a little more from around it. That makes it denser still, which makes its pull stronger still, which draws in yet more. Slowly, over enormous spans of time, the rich get richer. The dense regions grow denser, and the thin regions grow thinner, draining out into the gathering clumps. The smoothness very slowly curdles. The faint ripples deepen into real structure. This process has a name, and it describes the whole architecture of the cosmos. We call it gravitational collapse, or the growth of structure. And it is the slow, quiet engine that turns a smooth fog into a sky full of galaxies. But here's the thing, and it is the strangest turn in the whole story. So let me give it room to breathe. The ordinary matter, the hydrogen and helium gas, could not have done this on its own. Not in the time available. If all the universe had to work with was that visible gas, the ripples would have been far too gentle, and gravity would have worked far too slowly to gather galaxies together by now. The math simply does not add up. Something else had to be there. Something with much more gravity than the gas alone. Something that started gathering into lumps much earlier and much faster, and then quietly pulled the visible gas in after it. Something we cannot see and have never seen, and to this day do not fully understand. We call it dark matter. I know how that sounds. Dark matter. It has the ring of something invented to plug a hole, a fudge, a piece of science fiction smuggled into science. So let me tell you honestly how we came to believe in it, because it was not invented to be mysterious. It was forced on us, reluctantly, by careful people looking at the sky and finding that the numbers refused to work. The first hint came in the 1930s from a brilliant, prickly, often difficult astronomer named Fritz Zwicky, who was born in Bulgaria in 1898 and worked in California. In 1933, Zwicky was studying a great cluster of galaxies, hundreds of them, swarming together in a region of the sky in the constellation Coma Berenices. He measured how fast the galaxies in that cluster were moving, swirling around one another. And he found something that should not have been possible. The galaxies were moving so fast that the cluster should have flown apart long ago, scattering its members into the dark. The visible matter in it, all those stars and all that gas, did not have nearly enough gravity to hold the swarm together against such speeds. It was like watching a carousel spinning so fast that the riders should have been flung off into the field. And yet, somehow, they stayed on. Something invisible had to be holding them, some unseen mass providing the missing gravity. Zwicky gave it a plain German name. He called it dunkle Materie, dark matter. For decades, almost nobody took the idea seriously. It sat in the corner of astronomy, an awkward anomaly, easy to ignore. And then, in the 1960s and 1970s, it came back, this time impossible to dismiss. And it came back largely through the patient work of an astronomer named Vera Rubin, who was born in 1928 in Philadelphia, and who spent years being underestimated and excluded in a field that did not make much room for women. Rubin, working with an instrument builder named Kent Ford, studied the way individual galaxies spin. Not clusters this time, but single galaxies, like our own. She measured how fast the stars at the edges of a spiral galaxy were orbiting around its center. And here, let me give you an everyday picture, because the result is one of the clearest pieces of evidence we have. Think about our own solar system, the sun with its planets. The planets close to the sun, like Mercury, orbit very fast. The planets far out, like Neptune, orbit slowly, ambling along their great wide tracks. That is exactly what you would expect, because almost all the mass, almost all the gravity, is concentrated in the sun at the center. The further out you go from that central pile of mass, the weaker its pull, and the slower things orbit. It is like water swirling down a drain, fastest at the middle, lazier at the rim. Rubin expected to see the same thing in galaxies. The stars near the bright, crowded center should orbit fast, she thought. And the lonely stars way out at the faint edges, far from most of the galaxy's visible mass, should be dawdling along slowly. But that is not what she found. She found that the stars at the edges of galaxies were orbiting just as fast as the stars closer in. The outer stars were not slowing down at all. They were racing around at speeds that, by all the visible mass on display, should have flung them off into intergalactic space entirely. The galaxies were spinning as though they contained far, far more mass than anyone could see, and as though that extra mass was spread out in a vast, invisible halo, reaching out well beyond the bright disk of stars. Now, think about what that means. Every spiral galaxy you have ever seen in a photograph, that beautiful glowing pinwheel, is only the small, bright, visible center of something much larger. It sits inside an enormous, invisible cloud of dark matter, like a single bright candle flame sitting inside a vast, unseen room. The part you can see, all those billions of stars, is the minority. Most of the galaxy is the part you cannot see at all. And it is that invisible part, that dark scaffolding, that did the heavy lifting in the deep past. It was the dark matter that gathered first, that built the framework, that drew the visible gas in to make the stars. The galaxies we admire are, in a sense, just the luminous decoration hanging on a hidden structure. Let me give you one more picture for this, because it is the one I find most restful. Imagine, very early in the night, that someone hangs a string of fairy lights across a dark garden. From a distance, all you can see are the little bulbs, glowing, seeming to float in the black air, scattered in a graceful curve. You might think the lights themselves are the whole thing. But of course there is a wire, a thin, dark, invisible wire that the lights are strung along, holding them in their pattern, giving the whole arrangement its shape. You cannot see the wire in the dark. You only see the bulbs, but the wire is what holds the bulbs where they are. Dark matter is the wire. The galaxies, with all their stars, are the bulbs glowing along it. And the pattern of galaxies across the whole universe, the great web of them, follows the hidden wire of dark matter laid down in the very beginning. So now we can finally tell the early chapters of galaxy formation properly, with all the pieces in place. Let me take you back again, into the deep past, and walk it through slowly. After the fog lifted, after the universe became clear, there came a long, quiet stretch that astronomers call the cosmic dark ages. And the name is honest. For a long time, there really was no light being made anywhere. The afterglow of the beginning faded and stretched and cooled, sliding from a fierce brightness down toward a dull red, and then out of visible light altogether, into the cold dark. And no new light replaced it, because there were no stars yet to shine. The universe was filled with its thin gas, hydrogen and helium, drifting in the dark, slowly cooling, slowly gathering. If you had been there with human eyes, you would have seen nothing at all, just black in every direction, and a cold so deep it has no real comparison. The longest, quietest night there has ever been. But the darkness was not empty, and it was not idle. Beneath the surface, hidden from any eye, the dark matter was at work. Those faint ripples from the beginning, the gentle unevenness left in the dark matter, were deepening. The slightly denser regions were pulling themselves together, drawing in more and more dark matter, building up into vast, invisible clumps. We call these clumps halos. A dark matter halo is just a great gathered mound of the invisible stuff, held together by its own gravity, sitting in the dark. And all across the young universe, in the deep silence, these halos were forming. Small ones first, then small ones merging into larger ones, then larger ones merging into larger ones still. A slow, invisible coming together like raindrops on a window gathering into rivulets, the rivulets joining into streams, all of it sliding quietly downhill under gravity in the dark. And here is the lovely part. Wherever the dark matter gathered, its gravity made a kind of well, a dip in space that the ordinary gas could roll down into. The visible hydrogen and helium, drifting through the universe, felt the pull of those invisible halos and began to flow toward them, pooling in the bottoms of the wells, collecting where the dark matter was thickest. The dark matter built the basins. The gas filled them. It is, if you like, a story of invisible valleys being carved first, and then the rivers of gas finding their way down into them. The galaxies would form at the bottoms of those valleys, where the gas pooled deepest. Now, gas pooling in a well does not by itself make a star. Something more has to happen. The gas has to collapse, has to fall in on itself, has to compress and heat and squeeze, until, at its core, something ignites. And here we run into a delicate problem, the kind the early universe had to solve before it could make its very first stars. Let me explain it gently, because it is a beautiful piece of physics. When gas falls together under gravity, it heats up. You can feel a hint of this yourself if you pump up a bicycle tire quickly and notice the pump grow warm in your hand. Squeezing gas makes it hot, and hot gas pushes back. It has pressure, it wants to expand, it resists being squeezed further. So as the primordial gas tried to collapse into the dark matter wells, it heated up, and that heat fought against the collapse, holding the gas up, keeping it from falling all the way in. For a star to form, the gas needs a way to shed that heat, to cool down as it falls, to let go of the warmth so that gravity can keep pulling it inward. The gas needs to be able to radiate its heat away, like a warm cup of tea giving off its heat into a cold room until it can be held comfortably. But the very first gas was made of only hydrogen and helium, and these are not very good at cooling. They struggled to carry heat away. Later in the universe's history, gas could cool quickly and easily because by then it was laced with heavier elements, carbon and oxygen and the rest, which are wonderful at radiating heat into space. But in the beginning, none of those existed yet. So the first gas had to cool through a slow, awkward, inefficient process, and that made the first stars hard to form, and it shaped what they would be like when they finally did. Because gas that cannot cool well cannot fragment into many small pieces. It tends to collapse in big, heavy lumps. And big, heavy lumps make big, heavy stars. So the very first stars, when they finally ignited, somewhere around 100 to 200 million years after the beginning, were not like our sun. They were monsters, giants. Stars dozens, perhaps hundreds of times more massive than the sun, blazing with a fierce blue-white heat, burning through their fuel at a furious pace. We have never actually seen one. They lived and died long before any telescope existed, indeed long before the Earth existed. We call them by a slightly odd name, population 3 stars, for reasons of historical bookkeeping that do not matter tonight. What matters is what they were. They were the first lights. After the long dark ages, after the longest night, these enormous stars flickered on, one by one, in the bottoms of the dark matter wells. And for the first time since the fog lifted, the universe began to glow again with freshly made light. Picture that just for a moment as you lie there. The whole universe dark for 100 million years and more. And then, scattered across that darkness, the first stars catching fire. Not all at once, but here and there, a point of fierce blue light igniting in the black. And then another, and another, in the deep wells where the gas had pooled. The dawn of the cosmos. The first morning breaking very slowly, across the whole sky at once. in a universe that had known nothing but the dark. And these first stars did something that changed everything that came after. They cooked. Deep in their cores, under crushing pressure and heat, they fused the simple hydrogen and helium into heavier things. Carbon, oxygen, nitrogen. The elements that had been missing from the beginning, the ingredients for planets and for life, were being made for the very first time inside these giant early stars. And because the stars were so massive, they did not live long. A star that big burns through its fuel in just a few million years, a mere blink by cosmic standards. And then it dies. And it does not die quietly. It ends in a colossal explosion, a supernova, one of the most violent events in nature, briefly outshining an entire galaxy. And in that explosion, it flings all the new elements it has made out into the surrounding gas, seeding the young universe with carbon and oxygen and iron, enriching the plain hydrogen and helium with the makings of everything else. This matters enormously for our story. So let me say it slowly. Each generation of stars makes the next generation easier and different. The first stars enriched the gas with heavier elements, and that enriched gas could cool far more efficiently than the plain primordial gas had, which meant the next generation of stars could form more easily and in smaller pieces, making smaller, longer-lived, gentler stars, more like our sun. The universe was, in a sense, learning to make stars better, bootstrapping itself, one generation at a time, from a few rare giants into vast crowds of ordinary suns. And the places where all this was happening, these little knots of gas and the first stars gathered in the dark matter wells, were the first proto-galaxies, the seeds of everything to come. They were small and ragged and irregular, nothing like the grand spirals of today. But they were the beginning, the first galaxies, taking their first uncertain shape in the early light of the first stars. There is one more thing those early stars did, and it is the reason the cosmic dark ages finally ended for good. The fierce ultraviolet light pouring out of those hot young stars was powerful enough to do something to the gas around them. It could tear the electrons back off the hydrogen atoms, undoing, in a sense, the great clearing that had happened when the fog first lifted. This process spread outward from the early galaxies like bubbles expanding into the surrounding gas, bubble after bubble, growing and merging, until eventually almost all the hydrogen between the galaxies had been transformed. Astronomers call this stretch of time the epoch of reionization, which is a mouthful, but you can think of it simply as the time when the early galaxies, with their fierce young starlight, lit up the universe and cleared the last of the cosmic murk. It was the true end of the Dark Ages. After this, the universe was lit and transparent and full of galaxies finding their feet. And it has stayed that way ever since. So now we have our first proto-galaxies. Small, lumpy, glowing knots of gas and young stars sitting in their dark matter wells, scattered across the early universe. And I want you to let go now of any idea that a galaxy forms all at once, fully grown, the way a photograph might suggest. That is not how it happens. A galaxy is not built like a house, raised once and then finished. A galaxy is grown slowly over billions of years, mostly by joining with other galaxies. This is the single most important idea in the whole modern picture of how galaxies form. So let me give it plenty of room. The big galaxies we see today were built up from many smaller ones, merging together again and again over almost the entire history of the universe. We call this hierarchical assembly, small things forming first, and then combining into larger things, step by patient step. Let me give you the gentlest possible picture of it. Imagine a wide, still pond on a cold, quiet morning, and on the surface of the pond, scattered everywhere, are countless tiny drops of water and little flecks of mist. As the morning goes on, the nearest drops drift together and touch and merge into slightly larger beads. Those beads drift and merge into larger ones still. Wherever there is a slightly bigger pool, it pulls the smaller drops toward it and grows and pulls in more. Over time, what was a fine spray of tiny droplets becomes a scattering of larger pools, and then a few big ones, each one built from thousands of the small ones that came before. That is, very nearly how galaxies grow. The early universe was a fine spray of small proto-galaxies, and under the slow pull of gravity, guided by the dark matter scaffolding, they drifted together and merged again, the small ones building the medium ones building the great ones, across billions of years of quiet, gravitational drift. Now, the word merger might make you picture a violent crash. Two galaxies smashing into each other in a great, fiery collision. And in one sense, mergers are tremendous events, involving unimaginable amounts of matter. But here is something that may surprise you, and that I find strangely soothing. When two galaxies merge, the stars almost never actually hit each other, not even close. Think about how much empty space there is between the stars. If you shrank the sun down to the size of a grain of sand, the nearest star would be another grain of sand many kilometers away. Galaxies are mostly emptiness, with their stars spread impossibly thin through the dark. So when two galaxies pass through one another, the stars simply glide past each other, through the vast gaps, almost never colliding. It is less like two cars crashing, and more like two enormous, slow-moving swarms of fireflies drifting through one another in a dark field. Each firefly sliding silently between the others, the two swarms gradually tangling and blending into one larger swarm. What does get stirred up in a merger is the gravity and the gas. The two galaxies pull on each other with enormous force, and their once orderly motions get scrambled, their shapes pulled and stretched into long glowing streamers and bridges and tails of stars, flung out across space by the tides of the encounter. And their clouds of gas, unlike their stars, are big and soft and do collide, slamming together, compressing. And that compression triggers bursts of brilliant new star formation, the merging galaxies suddenly blazing with the light of countless newborn suns. Over millions of years, the two swirling swarms settle and merge, and find a new equilibrium and become a single, larger galaxy, often with a new shape entirely. This has happened over and over throughout the life of the universe. Every large galaxy you see is the descendant of many smaller galaxies that came together this way, including, as we will see, our own. Let me slow down and just let you rest in the scale of this for a moment, because I think it is one of the most beautiful things in all of science, and one of the most peaceful. These mergers do not happen quickly. A single major merger between two galaxies can take 1 billion years or more to fully play out, from the first gentle approach to the final settling. 1 billion years. That is more than 200 times longer than there have been human beings of any kind on the Earth. The galaxies are moving the whole time, of course, but so slowly against such vast distances that to any single moment, to any single lifetime, they would appear utterly frozen, utterly still. The grandest events in the universe are also among the slowest. A galaxy merger is a collision so gentle and so unhurried that it makes the slowest thing you have ever watched look frantic. The drift of continents is a sprint by comparison. There is something deeply restful in that, I think. The biggest things move the most slowly, The universe is in no hurry at all. And as these mergers and this slow gathering went on, across the first few billion years, the galaxies grew, and they began to settle into the broad kinds of shapes we recognize today. This is where we can ask one of the loveliest questions in the whole subject. Why do galaxies look the way they do? Why are some of them grand, flat, glorious spirals like our own, with their sweeping arms and bright central bulge? And why are others great, smooth, featureless balls of stars, with no arms and no disk at all, just a gentle glowing swarm? The shapes are not random. They are the fingerprints of each galaxy's history. And once you understand how they came to be, you can almost read a galaxy's life story from its shape, the way you might read something of a person's life from their face. Let me take the spirals first, because we live in one, and because they are, to my eye, the most beautiful things in the sky. A spiral galaxy is, at heart, a great flat disk of stars and gas, turning slowly, with a brighter bulge of older stars at its center, and graceful arms winding outward through the disk. The key word there is disk. The galaxy is flat, like a vast, slowly spinning plate. And the question is, why flat? Why should a galaxy settle into a thin disk rather than staying a shapeless blob? Here is the answer, and it brings back an everyday picture you already know in your body. It comes down to spin. As the gas first gathered into a proto-galaxy, it was almost never sitting perfectly still. It was always turning just a little, given a faint rotation by the tugs and pulls of everything around it. And as a spinning cloud of gas collapses, it does something you have seen a figure skater do, though I want to find our own version of it. So let me reach instead for a humbler picture. Think of stirring a mug of tea and then watching it settle. Or better, think of water draining from a wide, shallow basin. As the water flows down toward the drain, drawing inward, it spins faster, and it flattens out, and it forms a smooth turning sheet, a swirling disk, spreading wide and thin around the center. A collapsing, spinning cloud does the same. As it falls inward and spins faster, it flattens, because the spin resists collapse in the sideways direction, but does nothing to resist it up and down. So the cloud pancakes? It settles into a thin, wide, spinning disk. And that disk, full of gas, keeps forming new stars across its surface for billions of years, which is why spiral galaxies are full of young, bright, blue stars and bright clouds of glowing gas and ongoing birth. A spiral galaxy is a galaxy that settled gently, kept its gas, kept its spin, and never suffered too violent an upheaval. It is, in a sense, a galaxy that had a relatively calm life. The smooth, featureless balls of stars are a different story, and a more turbulent one. We call them elliptical galaxies, because they tend to be rounded, egg-shaped or ball-shaped, with no disk, no arms, no ongoing birth of stars. An elliptical galaxy is full of old stars, reddish and aging, with very little gas left to make new ones. It is a galaxy that has, in a sense, finished. And the leading idea for how the great ellipticals form is that they are the products of the most violent mergers. When two large spiral galaxies, each with its own orderly spinning disk, collide and merge in a major event, the violence of it scrambles everything. The neat disks are destroyed, the orderly spins canceled out and randomized, the stars flung into a chaos of orbits, pointing every which way. The gas is mostly used up in a great burst of star formation, triggered by the collision, or driven out of the galaxy entirely. And when everything settles, what is left is not a disk at all, but a smooth, rounded, slowly milling swarm of stars on tangled orbits, with little gas remaining to make anything new. An elliptical galaxy, then, is often a galaxy that lived a more dramatic life, that suffered a great collision, and came out the other side transformed, settled, and quiet. Where a spiral is a galaxy that kept its calm, an elliptical is frequently a galaxy that went through fire. Think about what that means, just for a moment. When you look at a galaxy, at its shape, you are looking at the visible memory of everything that happened to it. A graceful spiral is a galaxy that gathered gently and was left in peace. A great smooth elliptical is, very often, two grand spirals that met and merged and lost themselves in becoming something new. The shape is the history. And every galaxy in the sky, if you could only read it, carries the whole long story of its past written into its form. Now, I have been telling you this story as though it were tidy, as though it all clicks neatly into place. And I want to be honest with you, because the honest version is more interesting and, oddly, more restful. The truth is that galaxy formation is one of the messiest, most actively argued corners of all of science. And there are pieces of it that still keep researchers up at night. Let me show you a couple of the puzzles, gently, not to trouble you, but because there is something comforting in knowing that even the people who study this for their whole lives still find it wonderfully, humblingly unfinished. Here is the first puzzle, and it lurks at the very heart of nearly every large galaxy. If you travel into the center of a galaxy like ours, down through the crowded core, you find, at the very middle, something extraordinary. A black hole. Not a small one, of the kind a single dying star might leave behind, but a supermassive black hole with a mass of millions, or even billions, of suns, all packed into a single point of such intense gravity that not even light can escape it. Almost every large galaxy seems to have one of these monsters at its heart. Our own Milky Way has one, sitting quietly at its center with a mass of about 4 million suns. And the strange thing, the deeply puzzling thing, is that the size of a galaxy's central black hole is closely tied to the properties of the galaxy around it, even though the black hole is unimaginably tiny compared to the whole galaxy. It is as though the seed at the very center somehow knows about and is connected to the entire fruit grown around it. That relationship is a clue that the central black hole and the galaxy grew up together, influencing one another. But exactly how they did that, which came first, how they shaped each other, is still very much an open question. And black holes are not just passive passengers. When gas falls toward a supermassive black hole, it does not fall in quietly. It swirls into a fierce, blazing disk, heated to extraordinary temperatures, and a fraction of it is flung back out again in titanic jets and winds, pouring energy out into the surrounding galaxy. This pouring out of energy has a name, feedback, and it turns out to matter enormously. The energy from the central black hole can heat the gas in the galaxy or blow it away entirely, and gas that is too hot or simply gone cannot collapse to form new stars. So the black hole at the center can act like a kind of thermostat or a brake, regulating how many stars the galaxy makes, sometimes shutting down star formation altogether. It is a strange thought that the brightest, most violent object in a galaxy can be the very thing that quiets the galaxy down, that brings its star-making to an end. The thing at the center that should be most destructive turns out, in the long run, to be one of the things that shapes the galaxy most carefully. The universe is full of these quiet contradictions. Here is the second puzzle, and it is fresh, which is part of what makes it so exciting. For most of the last few decades, our deepest look back into the early universe came from the great Hubble Space Telescope, launched in 1990, which gave us our first real glimpses of young galaxies as they were billions of years ago. Because light takes time to travel, Looking far across space is the same as looking far back in time. When you look at a galaxy a billion light years away, you see it not as it is now, but as it was a billion years ago, when its light first set out toward you. The further away you look, the deeper into the past you see. And so a powerful enough telescope is also, in a sense, a kind of time machine, letting us look back toward the early universe by looking at the faint, ancient light of the most distant galaxies. In late 2021, a new and far more powerful telescope was launched, the James Webb Space Telescope. Named for a former administrator of the American Space Agency, and built to see further and deeper into the early universe than anything before it. It was designed especially to catch the faint, stretched-out light of the very first galaxies, the ones forming in the early universe. Light so ancient and so stretched by the expansion of space that only a telescope tuned to see warmth, to see infrared light, could detect it at all. And when this new telescope opened its eye and looked back toward the dawn of the galaxies, it found something that genuinely surprised the people who study this. It found galaxies that seemed too big and too bright and too grown up, too early. Galaxies that appeared to have assembled large numbers of stars far sooner after the beginning than the standard picture comfortably predicted. It was as though we had looked back to the universe's early childhood, expecting to find only scattered toddlers, only the smallest, faintest first proto-galaxies, and had instead found some surprisingly large and developed things already there, gathered together faster than the models said they should have been. Now, I want to be careful here, because this is exactly the kind of result that gets exaggerated. It does not mean the whole story is wrong. The broad picture, the smooth beginning, the dark matter scaffolding, the gathering of gas, the building up of galaxies by merging, all of that still stands on enormous and solid evidence. But the details of how fast the first galaxies grew, of just how quickly the early universe got to work building its bright structures, those details are being rethought right now, in real time, as the new data comes in. The story is still being written. We are, even tonight, living through a moment when our picture of the first galaxies is being gently revised, and that is not a flaw in the science. That is the science working exactly as it should, looking and being surprised, and looking again. I find that genuinely soothing in a way I did not expect. The idea that the universe still has the power to surprise the cleverest people who study it, that we have not finished, that there are people right now sitting up late with new images of the oldest galaxies, frowning, delighted, puzzled, revising. The story of how galaxies form is not a closed book in a library. It is a long, living conversation, still going on, and you have wandered into the middle of it tonight, and you are allowed to simply lie back and listen to it unfold without needing to settle anything at all. There is one more kind of object from the early universe worth pausing on, because it is the brightest thing of all, and it comes straight out of everything we have been saying about black holes and feeding and the growth of galaxies. In the young universe, when the first big galaxies were assembling and gas was pouring down into them in great quantities, some of those central black holes were feeding furiously. And a black hole that is feeding furiously is not dark at all. The gas spiraling toward it is squeezed and heated to such extraordinary temperatures just before it falls in that it blazes with a light brighter than the entire galaxy around it, brighter than hundreds of ordinary galaxies put together. These brilliant, feeding hearts of young galaxies have a name. We call them quasars, and they are among the most luminous objects in the whole universe. When astronomers first found quasars decades ago, they were baffled by them, because they looked like faint stars. Yet their light showed that they were unimaginably far away, which meant that to be visible at all at such distances, they had to be pouring out staggering amounts of energy from a very small region. It took years to work out what they were. Now we understand. A quasar is a young galaxy with a feeding supermassive black hole at its core, blazing as the gas falls in. And because they are so bright, we can see them across almost the entire universe, all the way back toward the early days of galaxy formation. They are like distant lighthouses, scattered through the deep past, marking the places where the first great galaxies were assembling, and their central black holes were drinking deep. What I find lovely about the quasars is what they have become. Almost all of them are in the past. The universe was full of brightly blazing quasars when it was young, when there was abundant gas pouring into the young galaxies. But as the universe aged, and the easy gas was used up or settled down, the feeding slowed, and the great beacons dimmed, one by one. The quasars are mostly gone now, fallen quiet. The furious feeding hearts of the young galaxies have, for the most part, settled into stillness. Our own Milky Way's central black hole is one of them, almost certainly. In its youth, when our galaxy was assembling and gas was plentiful, it may well have blazed as a quasar, one of those distant lighthouses, visible across the universe. And now it sits quietly at our center, dim and calm, having long since finished its fierce feeding, a sleeping giant where once there may have been a beacon. The brightest objects in the history of the universe, gone gentle with age. There is something in that, too, to rest on. Even the fiercest things grow quiet in time. So let us come home now. Let us turn away from the distant galaxies and the early universe, and come back to our own galaxy, the Milky Way, the one whose soft band you might see arching over you on a dark night. Because everything we have talked about, the dark matter scaffolding, the pooling gas, the first stars, the long, slow gathering by merger after merger, all of it happened here too. Our galaxy has a history, a real and surprisingly eventful one. And in the last few years, we have begun to read it in remarkable detail by studying the motions and the chemistry of the stars around us. The Milky Way is old. Its oldest stars are nearly as old as the universe itself, formed within the first billion years or so after the beginning. And like every large galaxy, it was not born at its present size. It grew mostly by swallowing smaller galaxies, again and again, over billions of years. We can actually find the evidence of these ancient meals written into the population of stars around us. There are whole groups of stars in our galaxy that move together in distinctive ways and that have a distinctive chemistry, marking them out as not native to the Milky Way at all, but as the remains of smaller galaxies that our galaxy drew in and tore apart and absorbed long ago. Their stars are still here, woven now into the body of the Milky Way, but their shared motions remember, faintly, that they once belonged to somewhere else. One of the largest of these ancient meals happened roughly 10 billion years ago, when the young Milky Way merged with a smaller galaxy. Astronomers have given that swallowed galaxy a name, drawn partly from old mythology, and they have been able to identify the stars that came from it. Scattered now throughout the inner halo of our galaxy, a ghostly population still tracing, in their orbits, the shape of a collision that happened before the Earth existed. There is something quietly moving in that. Some of the stars you might see on a clear night did not begin here. They came from another galaxy entirely, one that no longer exists, one that our Milky Way absorbed in the deep past, and they have been part of us ever since. Their origins remembered only in the patient curve of their orbits through the dark. And the merging is not finished. Even now, the Milky Way is in the slow process of pulling in and absorbing smaller companion galaxies. There is a small galaxy called the Sagittarius dwarf on the far side of our galaxy's center that is being gradually torn apart and woven into the Milky Way as we speak. Its stars stretched out into long streams that wrap around our galaxy like ribbons. Our galaxy is still eating, still growing, still gathering itself by the same slow process that built it in the beginning. The story we have been telling of small things merging into larger things is not safely finished and tucked away in the past. It is happening here, around us tonight, only so slowly that across all of human history, it has barely seemed to move at all. And if we look far enough ahead, there is a much larger merger waiting in our future. One that brings us right back to where we started this whole long story. Remember Andromeda, the spiral galaxy whose distance Edwin Hubble measured to prove that other galaxies exist? Andromeda is our nearest large galactic neighbor, a grand spiral much like our own. And it is not moving away from us the way most galaxies are. It is moving toward us. Slowly, across the immense gulf between us, Andromeda is approaching, drawn by the gravity that binds our little group of galaxies together. And in something like 4 to 5 billion years from now, those two galaxies may meet. For a long time, astronomers spoke of this as a certainty, a collision written firmly into the future, a head-on meeting that would scramble both galaxies and settle them, over a span of perhaps a billion years more, into a single larger one. But the honest, up-to-date picture is gentler and less certain than that. In 2025, a team led by the astronomer Til Sawala, working with the most precise measurements yet from the Gaia and Hubble space telescopes, ran the possibilities many thousands of times over, and found that the outcome is closer to a coin flip. There is roughly an even chance the two galaxies will merge within the next 10 billion years, and roughly an even chance they will simply pass each other by or never quite meet at all. The gentle pull of the other galaxies nearby, the smaller members of our local group, nudges the result one way or the other, and we cannot yet say which. For now, the fate of our galaxy is, in their own words, still completely open. Let me set your mind at ease about all of this, in case it sounds at all unsettling as you are trying to drift off. Whatever happens, it is nothing to fear, and nothing that any living thing on Earth will ever witness, because it lies billions of years away, further in the future than the entire age of the Earth so far. And remember what we said about mergers. The stars almost never collide. If the two galaxies do come together, and if anyone is somehow still here to see it, they would witness the most extraordinary, slow, silent transformation of the night sky. Andromeda swelling across the heavens over hundreds of millions of years, the two galaxies winding together in a vast, patient embrace, with hardly a single star striking another. And should that merger come to pass, the Milky Way would in time become an elliptical galaxy, spiral grace giving way to the smooth, settled quiet of a galaxy that has lived a full and eventful life. Whether it happens or not, the same long story keeps unfolding around us, with no real ending in sight. Now, let's slow down even further, because I want to bring this whole vast story right down into the room with you, right down into the bed you are lying in, into your own hands resting on the blanket. Because there is a connection between the formation of galaxies and your own body that is so direct and so literal that when people first understand it, they sometimes go quiet for a while. Remember what we said at the very beginning. The early universe made almost nothing but hydrogen and helium. None of the heavier elements existed yet. No carbon, no oxygen, no nitrogen, no calcium, no iron. And yet, your body is full of these things. The carbon in every cell of you. The oxygen you are breathing in and out. Slowly, right now. The calcium that makes your bones, the iron that lets your blood carry that oxygen around. Where did all of it come from? It was not there at the beginning. It had to be made. And the only place in the entire universe where these elements are made is inside stars, and in the explosions that end the lives of the largest stars. Carbon and oxygen are forged in the cores of stars over their long lives. Heavier elements, like much of the iron and gold and many of the rest, are made in the violence of supernovae and in the collisions of the dense dead cores that some stars leave behind. So every heavier than helium atom in your body was made inside a star that lived and died before the sun was born. Atoms cooked in the hearts of ancient suns, flung out into space when those suns exploded, drifting through the galaxy for ages, mixing into clouds of gas and eventually gathered up again, along with countless others, to form a new star, our sun and the planets around it, and the earth and the seas, and in time, living things, and in time, you. You are, quite literally, made of the ashes of dead stars. And those stars could only exist because there were galaxies for them to live in. Without galaxies, the gas would never have gathered densely enough to make stars at all. Without the long, slow building of galaxies that we have been following all this time, there would be no stars to forge the elements, and so there would be no Earth, and no you. The story of how galaxies form is not a distant story about faraway things. It is the story of how the material of your own body came to be. When you look up at that soft band of light, you are, in a real and not at all poetic sense, looking at the kind of place where you were made. Let that settle for a moment. The iron in the blood moving through you right now was made inside a star, in a galaxy, in the deep past. You are not separate from the night sky. You are a small, warm, breathing piece of it that has gathered itself together for a little while and become able to look back up and wonder where it came from. There are not many thoughts as large as that, and not many, I think, as gentle. And there is one more scale I want to take you to, the very largest, before we begin to wind down. Because galaxies, it turns out, are not scattered randomly through space. They are not sprinkled evenly, like salt across a table. When astronomers carefully map out the positions of millions of galaxies across the universe, a breathtaking pattern emerges. The galaxies are strung together into long, glowing filaments, like threads. And the filaments meet at dense knots where great clusters of galaxies gather. And between the filaments, there are vast, almost empty voids, immense dark bubbles of nearly nothing, with the galaxies draped over their surfaces. The whole universe, on the largest scale, looks like a kind of foam or a web, or the inside of a sponge. We call it the cosmic web. Strands of galaxies threading through an enormous darkness with the great voids in between. And here is the thing that ties it all together, the thing I find most beautiful of all. That web, that vast pattern of filaments and knots and voids, is not random either. It traces, on the grandest scale, the scaffolding of the dark matter, which traces, in turn, all the way back to those faint ripples in the early universe, the tiny variations in that oldest light, the cosmic microwave background. The whole magnificent structure of everything, the spider's web of galaxies spanning the visible universe, grew from the gentlest imaginable unevenness in the smooth beginning. Those tiny ripples, smaller than a fraction of a degree, were the seeds of all of it. Pull on any thread of the great cosmic web, and it leads you back eventually to the faintest texture in the afterglow of the beginning. The largest structures in existence are the grown-up form of the smallest possible imperfections in the dawn. There is something almost unbearably gentle about that. Everything grand, everything vast, everything that holds the galaxies in their great glowing patterns began as a whisper. Let's slow down now and gather the whole story up in our arms, gently, and look at it all together. From a little distance, the way you might look back over a long walk from the top of a hill. Because we have come a very long way tonight, and there is no harm at all in walking back through it slowly, letting each part settle, the way you let the events of a long day settle as you lie in the dark before sleep. It began with smoothness, a universe born hot and dense and almost perfectly even, expanding and cooling, expanding and cooling. In its first few minutes, it cooked the simplest ingredients, the hydrogen and the helium, and almost nothing else. For a few 100,000 years, it stayed a glowing fog, too hot to see through. And then it cleared, and the oldest light was set free to wander, the afterglow we still find filling the sky. The universe was smooth, but not perfectly smooth. It carried the faintest texture, the gentlest ripples, and that was enough. Then came the long dark, the cosmic dark ages, when no stars yet shone, and the only thing happening was the quiet, invisible gathering of the dark matter, deepening those faint ripples into wells, into halos, into a hidden scaffolding spread across all of space. And the ordinary gas, the hydrogen and helium, flowed down into those wells, pooling where the dark matter was thickest, gathering in the bottoms of the invisible valleys. And in those pools, at last, after the longest night there has ever been, the first stars caught fire. Enormous, fierce, blue-white giants, blazing in the dark, the first morning of the universe breaking very slowly across the whole sky. Those first stars cooked heavier elements in their cores, and when they died, they flung those elements out into the gas, seeding the universe with the makings of everything richer and more complicated to come. Each generation of stars made the next one easier, gentler, more ordinary. And the little knots of gas and stars, gathered in the dark matter wells, were the first proto-galaxies, the small, ragged seeds of everything. They lit up the universe, cleared away the last of the murk, and began the slow, patient work of growing. And they grew the only way galaxies ever grow, by gathering together, by merging again and again, small ones into medium ones into great ones, over billions of years, guided by the dark matter scaffolding, drawn together by the endless patient pull of gravity. Not in violent crashes mostly, but in slow, silent, billion-year embraces. Two swarms of stars drifting through one another, almost none of them ever touching, blending gradually into a single larger swarm. And as they gathered, they took their shapes. The ones that settled gently kept their gas, and kept their spin became the grand flat spirals, still making new stars across their turning disks. The ones that suffered the most violent mergers became the smooth, settled ellipticals, their disks scrambled, their gas spent, full of old red stars and quiet. The shape of each galaxy a record of its history, written for anyone who learns to read it. And in among all of this, at the heart of nearly every great galaxy, a supermassive black hole somehow grown up alongside its galaxy, sometimes blazing, sometimes feeding, sometimes quietly regulating how many stars its galaxy could make. And all of it, all the galaxies, strung together across the universe into the great cosmic web, the filaments and knots and voids, the largest pattern there is, grown from the smallest ripples there ever were. That is the whole arc of it. Smoothness, then ripples, then dark gathering, then first light, then the long, slow building by merger after merger, into the spirals and ellipticals and the great web we see tonight. It is one of the slowest, grandest stories ever pieced together. And the remarkable thing, the thing I want you to carry into sleep, is that we pieced it together at all. That creatures living for a few decades on a single small planet, near a single ordinary star, in the outskirts of one ordinary spiral galaxy, somehow worked out the history of the galaxies, going back nearly 14 billion years, mostly within the last 100 years or so. And it was real people who did it, with real names. And I would like to say them once more, softly, the way you might thank the people who built a road you have walked along. Henrietta Swan Leavitt, working patiently through her photographic plates, finding the rhythm in the pulsing stars that would become the measuring stick for the universe. Edwin Hubble, on his mountaintop with a great telescope, measuring the distance to Andromeda, proving the galaxies real, and then finding them all racing apart, which pointed back toward a beginning. Fritz Zwicky, prickly and brilliant, noticing that the galaxies in a cluster moved too fast for the visible matter to hold them, and naming the dark matter no one wanted to believe in. Vera Rubin, patient and overlooked, measuring the spin of galaxy after galaxy, finding the unmistakable fingerprint of that same dark matter, and finally making the world take it seriously. Arno Penzias and Robert Wilson, chasing an annoying hiss in their antenna, and finding the oldest light in the universe instead. And the countless others, unnamed tonight, who built the telescopes and wrote the equations and ran the long calculations and are sitting up even now with the newest images of the oldest galaxies, frowning and delighted and revising. The story belongs to all of them. And now, for a little while, it belongs to you too. There is one last gentle thought I want to leave you with before we let the words slow all the way down and stop. It is about time, and about how small and warm a thing it is to be alive inside a story this long. The galaxies took billions of years to form. The Milky Way is still gathering itself, still slowly eating its smaller neighbors, still drifting toward its distant meeting with Andromeda. An event so far in the future that the whole of human history, everything that has ever happened to anyone, is less than the blink of an eye against it. Against that immense slow clock, your life is brief, almost beyond measure. And yet, here you are, made of the ashes of ancient stars, gathered together for this little while into something that can breathe and rest and look up and wonder. The universe spent nearly 14 billion years, and untold galaxies, and generations of dying stars quietly assembling the atoms that became you. And tonight, those atoms are lying here, warm and safe, listening to the story of where they came from. That is not a small thing. That is perhaps the most remarkable thing of all. But we are not quite ready to stop yet. The night is long, and there is no hurry. And I would like to take you on one more slow, gentle walk before the words finally settle. Let us walk in our imaginations through our own galaxy, the Milky Way, and simply notice what kind of a place it is now that we know how it came to be. Because it is worth lingering over, the way you might linger in the rooms of a house you have just learned the history of, seeing it freshly. Picture the whole galaxy from far away, hanging in the dark. A great flat disk of stars, perhaps 100,000 light years across, turning slowly, with its bright spiral arms winding out from a glowing central bulge. At the very middle, hidden in the crowded core, the quiet, supermassive black hole, 4 million times the mass of the sun, sitting in the dark like a still point at the center of a turning wheel. And around the whole disk, reaching far beyond the visible stars, the vast, invisible halo of dark matter. the hidden scaffolding that holds it all together, the unseen room in which the bright candle of the galaxy sits. Now drift closer, into the disk itself. The spiral arms are not solid things, not really. They are more like slow waves, regions where the gas piles up a little and the birth of new stars is busiest, lit up bright and blue by the young hot stars forming there. Between the arms it is dimmer, older, quieter. The disk is where the gas lives, and so the disk is where new stars are still being born, all the time, in great glowing clouds of gas that astronomers call nebulae, the nurseries of the galaxy, where gravity is still pulling the gas together into new suns, exactly as it has been doing for billions of years. The galaxy is not finished. It is still making itself. Somewhere in the Milky Way, tonight, in some quiet cloud of gas, a new star is gathering, slowly, in the dark. And our own sun sits out in the disk, far from the crowded center, about halfway out toward the edge, in a fairly calm and ordinary neighborhood, on the inner edge of one of the spiral arms. There is nothing special about our position. We are not at the center of anything. We are simply tucked into a quiet corner of an ordinary spiral galaxy, going around the center once every couple of 100 million years in a slow, vast, patient orbit. The sun has gone around the center of the galaxy only about 20 times in its entire existence. Think about that. In the whole life of the sun, more than 4.5 billion years, it has made only 20 slow laps of the galaxy. The galactic year is so long that the sun has lived through barely a handful of them. There is something deeply calming in that, in being a small thing carried along in so slow and so great a turning. And out beyond the disk, in the halo that surrounds it, there are the oldest things of all. Great spherical swarms of stars called globular clusters, each one a tight ball of hundreds of thousands of ancient stars, bound together by gravity, orbiting far out around the galaxy's center. These clusters are among the oldest objects in the Milky Way, some of them nearly as old as the universe itself. Formed in the galaxy's earliest days, or even gathered in from the small galaxies our Milky Way swallowed long ago. When you look at a globular cluster, you are looking at a piece of the deep past, a relic of the galaxy's childhood, still circling quietly in the dark, full of old red stars that have been shining steadily since before the Earth was a thought in the universe's mind. So that is our home. A great slow turning disk of stars and gas, still giving birth, wrapped in a halo of ancient clusters and invisible dark matter, with a quiet giant at its heart, drifting through space, slowly merging with its neighbors, on its way, in the far future, to meeting Andromeda and becoming something new. And we are a single warm point within it. Near the edge, looking out through the thick of the disk at that soft band of light, which is simply our own galaxy, seen from the inside. The same river of stars Galileo first resolved through his little telescope 400 years ago. Everything we have talked about tonight is contained in that pale band you might see overhead. The whole story, written in light, arching across the sky, waiting patiently for anyone who looks up to wonder about it. I should be honest with you about something now, in this quiet, because honesty belongs in a story like this, and because I think it is one of the most peaceful things of all. For all that we have learned, for all this grand and well-tested story, there are things at the very heart of it that we still do not understand at all. And I do not say that to unsettle you. I say it because there is a particular kind of rest that comes from sitting comfortably inside a mystery, without needing to solve it. We do not know what dark matter actually is. We have told its whole story tonight. The scaffolding, the halos, the wells the gas pooled into, and every word of that is supported by mountains of careful evidence. We can see its gravity everywhere, bending light, holding galaxies together, shaping the cosmic web. But we have never caught a single particle of it. We do not know what it is made of. It is not made of the ordinary stuff that you and the stars and the planets are made of. It is something else, something that does not give off light or absorb it, or interact with ordinary matter in almost any way except through gravity. People have built extraordinarily sensitive detectors, deep underground, in old mines and tunnels, waiting in the silence for a single particle of dark matter to brush against them. And so far, nothing. The most common kind of matter in the universe, the stuff that built the galaxies, and we do not know what it is. It is everywhere, and it is invisible, and it is, for now, a mystery. And there is a second mystery, larger and stranger still, that I will only mention gently, because it is enough to know that it is there. The expansion of the universe, the swelling of the dough that carries the galaxies apart, is not slowing down, as you might expect gravity to make it do. It is speeding up. Something is pushing the universe apart, faster and faster. And we do not know what that is either. We have given it a placeholder name, dark energy, which is really just a way of admitting that we have noticed something enormous happening and cannot yet explain it. Between the dark matter we cannot identify and the dark energy we cannot explain, the honest truth is that the overwhelming majority of the universe is made of things we do not understand. The galaxies, the stars, the planets. You, all the ordinary visible matter. The part of the universe we actually comprehend is only a small fraction of the whole. Most of everything is still a mystery. I find that somehow the most restful thought of all. Not frightening. Restful. Because it means the universe is still vast beyond our understanding, still holding its largest secrets close, still far bigger than anything we have managed to map. We have learned so much, an astonishing amount, enough to tell the whole long story of the galaxies. And we still stand at the edge of an immense unknown, having lit only a small clearing in a very large dark. There is something gentle in being a small, curious creature, lying in the dark, knowing a little, wondering at the rest, and not needing tonight to know any more than that. Before we begin to wind all the way down, there is one more gentle thing worth noticing, and it gives a softer, truer shape to the whole picture. When most of us imagine galaxies, we picture the grand ones, the great spirals, sweeping and bright, the huge ellipticals, smooth and stately, the famous photographs. But those are not the typical galaxies at all. They are the rare giants, the largest and brightest, the ones easy to see and easy to photograph. The vast majority of galaxies in the universe are something much smaller, much fainter, and much quieter. We call them dwarf galaxies. And they are, by far, the most common kind there is. A dwarf galaxy might hold only a few million stars, or a few 100 million, instead of the hundreds of billions in a galaxy like ours. They are dim and small and modest, scattered everywhere through the universe, often gathered around the larger galaxies like ducklings around a parent. Our own Milky Way has dozens of these small companions, faint clouds of stars circling us in the dark, most of them so dim that they were only discovered recently, with patient searching. And they matter enormously to our story, because remember how galaxies grow. By gathering, by merging. The great galaxies were built up in large part by swallowing these smaller ones, one after another, across billions of years. The dwarfs are not only the most common galaxies, they are also, in a sense, the building blocks, the bricks from which the giants were made. Every great galaxy is, in part, a great many small galaxies, gathered together and woven into one. There's something I find quietly moving in that. The galaxies that get all the attention, the magnificent spirals and the grand ellipticals, owe their very existence to the countless small, faint, overlooked galaxies that came before them and were drawn in to make them. The giants are built from the modest. The bright are made from the dim. And many of those small galaxies are still out there. The ones that have not yet been swallowed, drifting in the dark, faint and patient, holding their few million old stars, having taken part in the great building of the universe simply by existing, by gathering a little gas, by lighting a few stars, by waiting. Not every galaxy has to be grand to matter. Most of them never became spirals or giants at all. They simply formed quietly and shone faintly, and either drifted on alone or gave themselves up to make something larger. There is a whole universe of small, unremarkable, essential things, and they are the majority. And the giants could not exist without them. So when you picture the universe now, do not picture only the great glowing wheels. Picture also the multitude of small, faint things scattered between them and around them. The dwarf galaxies, dim and patient and uncountable. The quiet majority of all the galaxies there are, they are part of the story too, perhaps the largest part. And there is room in this vast, slow history for the small and the faint and the overlooked, which is, I think, a gentle thought to carry towards sleep. Let us return, one last time, to the simple act we started with. Lying still, looking up at that soft band of light. Because there is something about looking at the night sky, now that we have walked through all of this, that I would like to put into your mind as you drift towards sleep, something quiet to hold. When you look up at a galaxy, even just at the faint smudge of Andromeda on a dark night, you are not seeing it as it is. You are seeing it as it was, a very long time ago, when the light you are catching first left it. Andromeda's light has been traveling for about 2.5 million years to reach your eye. So when you see it, you are seeing light that set out before there were any modern humans at all, before our species existed, crossing the immense dark between the galaxies all that time, just to arrive, tonight, at the back of your eye. To look at the sky is to look into the past. Every point of light up there is a small window into a different moment of history. The nearer ones showing you the recent past, the furthest ones showing you the deep, deep past, almost back to the beginning. The night sky is not a picture of how things are. It is a vast, layered photograph of how things were. All the different moments arriving together, woven into a single quiet view. And this is how we learn the whole story we have told tonight. Not by traveling anywhere, but by looking, by catching the ancient light of distant galaxies and reading the history written into it. The further out we look, the further back we see. And so by looking at galaxies at many different distances, we look at galaxies at many different ages. And we can watch, in a sense, the whole process of galaxy formation laid out across the sky, like a single great family photograph that contains the newborns and the children and the grown adults and the very old, all at once. The nearby galaxies show us the present. The distant ones show us the past. And the most distant of all, the faintest, most stretched out light, caught only by our newest and most patient telescopes, shows us the very first galaxies, taking their first uncertain shape in the early light of the universe. We have, in this strange and beautiful way, watched the galaxies grow up by looking out across space and back across time, all from a single small planet, simply by paying very close attention to the light. Think about what a gentle kind of power that is. We never went anywhere. We could not go anywhere. The distances are so vast that no ship we could ever build could cross even the smallest part of them in 1,000 lifetimes. And yet, just by looking carefully, just by gathering the faint old light that falls on us freely every night, we worked out where the galaxies came from, and how they formed, and what we ourselves are made of, and where we sit within it all. The whole grand history, recovered by patient looking. There is a lesson in that, I think, somewhere, about how much can be learned by simply paying close, quiet, unhurried attention to what is already in front of you. But it is late, and lessons can wait for the morning. Tonight, it is enough simply to feel the wonder of it, and to let it carry you down. And here is the last thing I will give you to rest on, before the words begin to slow and soften and fade. It is about deep time, and about how kind a thing it can be to feel small inside it. We have spoken tonight in billions of years, so casually, so often, that the number may have stopped meaning anything, which is fine, because the feeling underneath it is what matters. The galaxies formed across spans of time so vast that no human mind can truly hold them. The slowest events we described, a single galaxy merger, take longer than the entire history of life on Earth. The universe is patient beyond all imagining. It is in no hurry at all. It has never been in a hurry. It took its time over everything, the cooling, the clearing, the gathering, the first stars, the long, slow building of the galaxies. None of it rushed, all of it unfolding at its own unhurried pace across the deep dark of time. And there is something in that, I think, that the body recognizes late at night when it is tired and ready to let go. The permission to be slow, the permission to let things take as long as they take. You do not have to solve anything tonight. You do not have to finish anything, or understand anything, or carry anything forward. The universe spent 14 billion years and never once hurried. And it would not ask you to hurry now, here, in the dark, at the quiet end of your day. You are allowed to be as slow as the galaxies. You are allowed to simply drift and gather yourself and rest. So let yourself begin to settle now, all the way down. There is nothing left to do. The story is told, or enough of it, and the rest can keep until another night. Feel the weight of your body against the bed, or the chair, or wherever you are resting. Feel how the surface beneath you holds you up, completely, asking nothing of you, so that you do not have to hold yourself up at all. Let your shoulders drop a little further than you thought they could. Let your jaw soften. Let your hands lie open and still. Notice your breathing without changing it. Just let it go on, slow and easy, the way it wants to, in and out, like something that knows what it is doing and does not need your help. The same kind of slow gathering and releasing that the galaxies have been doing all along, only smaller and warmer and closer, right here in your own chest, in the dark, in this room. And think, if you like, as you drift, of where all of this is happening. You in your room, in your bed, on the Earth, going around the sun out near the edge of the Milky Way, going slowly around the galaxy's center once every couple of 100 million years. The galaxy itself, turning and drifting through the local group of galaxies, slowly approaching Andromeda across the immense dark, and all of it strung along the great cosmic web. The threads of galaxies woven across the universe, grown from the faintest ripples in the oldest light, expanding gently outward, taking its time, in no hurry, going on and on into a future further away than we can see. You are a small, warm point inside all of that turning, held by gravity, made of ancient starlight, lying still in the quiet at the end of an ordinary day. The galaxies took nearly 14 billion years to gather themselves into the soft band of light above you. And tonight, you do not have to do anything at all, but rest beneath it. Let the numbers go. Let the names go. Let the whole story go. Gently, the way the universe lets go of nothing and holds on to everything. Slowly, patiently, in the dark. There is no next thing. There is only this. The weight of you and the slow tide of your breath, and the long, quiet turning of everything around you, carrying you, softly, down into sleep. Rest now. The galaxies will keep turning whether you watch them or not. And they have been waiting a very long time for a night exactly this quiet. Good night.